Okay, now I'm recording. And you can see that. Okay, so now we're going to get into water and water potential. So there are a handful of slides at the start of this slide set I'm not going to go into with you in class. You're expected to study that on your own. And it's basics of water, the water molecule. So it's refreshing you from Chem 111, 112. So that should just be a simple refresher for you. I'm going to jump ahead to this slide, water properties. So this water is an amazing substance, and plants, of course, just like any living organism, have to have water on a regular basis. So a couple of ideas about water that you need to think about heavily is this idea of cohesion, where you're thinking about the attraction of water molecules to each other, all right, based on their chemical nature, partial positive and negative charges on the water molecule. And so they are attracted to each other by the positive negative attraction. So think about that. That really does provide the situation for surface tension to arise on the body of a water. I love to think about that when I'm swimming at inland lakes in particular, when I can stay in longer than I can in Lake Superior. And I like to swim and then get my eyes right to the eye level and watch the insects skate across the lake. I just love watching them. The other weekend, they were just going nuts. Hundreds of insects swimming and skating across the lake. And it's because of that surface tension on the surface of the lake that allows them to do that, so they don't poke through and drown. Oh, I did watch I don't know my insects. I never took an insect class, but it was a small little insect that accidentally dropped on the surface of the water. It was a spider. And my son and I are like, go, 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 because you could see it swimming toward the shore. And we were like, rooting it on, hurry, hurry, hurry. And then a minnow comes up and wham. It's like, sorry, he didn't make it. But anyways, he was skating across that surface because of that surface tension, that interface between the surface water molecules of the lake and the air molecules creates this situation where the water molecules on the surface are more attracted to the water molecules below them than they are to the air above them. And it creates this membrane-like surface, so to speak, across a lake, Still Lake in particular. And so we need to think about that a little bit. And then tensile strength as well, which sounds weird to think about when you're talking about water, liquid water, because usually I think about tensile strength of like steel. If they're going to be building some skyscraper, you have to know the tensile strength of the different metals and so forth. But water can display tensile strength as well. And if you think about the idea of putting water into a hypodermic, the plunger part where you suck up the water, and then if you keep sucking back with the plunger, you're creating a tension on the water column. And it's like, well, how much tension can you apply to that before the water column breaks and you get a bubble in the mix? So essentially, you can do tensile strength with liquids. And water has a pretty good tensile strength as well. But plants, sometimes they push that beyond the tensile strength of water, given the situation they're under, and you can get air bubbles pop into columns of water inside the plant body, which can be not a good thing for plants. It's analogous to an embolism that you would experience in your blood vessels. And I think we all know embolisms are not a good thing, right? And so we'll get into that a little bit as well with plants. So adhesion is another property I want you to think about. That is the attraction of water to a solid phase, a solid surface. For our purposes, I'd like you to zero in on the idea of the vascular tissue in the plant, particularly the tissue that conducts primarily water and dissolved minerals. So vascular tissue, there's two major types of vascular tissue. Which one is for water transport? Xylem, all right, xylem. So we're thinking about the walls of the xylem. Remember, those cells are dead at maturity, so we don't have to worry about cytoplasm issues and all that. It's like a hollow straw system that is coursing through the plant body, analogous to blood vessels. And you have water coursing through that. And some of the water molecules that are, flowing past the wall of the xylem cells, there is going to be that adhesion force to think about. Okay, so when we look at movement of water through the plant body, let's zoom in on the xylem. Okay, so one of the first ideas they were thinking about is, water diffusing through the plant body. So you've learned about diffusion laws and how things diffuse. People give the example of, you put a sugar cube into coffee and watch it dissolve in the diffusion process, or you open a perfume bottle and the molecules get into the air and diffuse from the bottle out into the room. Well, Fick is the scientist who formally defined it. And so here you're seeing the equation on the top. And the thing I want you to, so the J is standing for diffusion, rate of flow, and then delta C over delta X is, the C is standing for concentration between 2 points that you're studying, 2 physical points. All right, so delta C over delta X is a difference in concentration in 2 areas that you're interested in studying. And so you can see that the rate, J, the rate of diffusion, is proportional to the concentration gradient between 2 points that you're studying, 2 physical areas. All right, so the J is the rate of solute transport. And then the D is just a diffusion coefficient that you can look up and plug into this equation. All right, and then the delta C over delta X, that's your concentration gradient. Now, I'm not going to ask you to memorize this to the point of spit this back to me. I just want you to think about diffusion processes, and that is proportional to delta C over delta X. All right, but I'm not actually going to make you do math and figure something out in that regard. All right, but the concept is important. So they were looking at how does water and its dissolved minerals move around in the plant, and they had to really, get into the very basics of this idea, and they were doing some calculations. They could measure water flow through the xylem, for example, and if you take Fick's first law and do a derivation of it, you can solve for how long it takes for something to diffuse across some distance. Okay, so this is the equation. And again, I'm not going to ask you to do that. It's just important that you understand that the time it takes, T, is equal to the square of the distance. Okay, not just distance, but the square of the distance. Okay. K, again, is just a constant that you can plug into the equation, and D is your diffusion coefficient. Again, that's just a number that you can look up. Both of those, you can look them up and plug them in. So they started doing some experiments where they were measuring how long does it take for something to move in that dissolved water a certain distance in the leaf, or they usually picked leaves because it was easiest to work with. And they could see that diffusion in the plant body can happen very quickly over really short distances. It works. You can say that this is moving via diffusion laws, okay? However, if they were tracking some movement of the plant, of the water, they usually put like a radioactive tracer in it, and they could say, oh, how long does it take to go a longer distance through the plant body? And then if they tried to apply the laws of diffusion, it broke down. It didn't work. So they knew diffusion wasn't going to work over long distances, because they could measure rapid movement over long distances, and they're like, yeah, that's too rapid. Diffusion doesn't account for that. There's something else going on besides diffusion. And so when they did the actual calculation of it, based on their experiments of how long does it take to get this tracer the length of a leaf, if they based it solely on diffusion laws, it would take 32 years for that substance to move the length of the leaf. And of course, that's not how it works in a plant. Plants is, some plants, they actually worked with corn, I think, on this. And of course, corn is just stays alive over the several months. So they had to kind of throw that out and go, okay, diffusion, the laws of diffusion work well in the plant if you're talking about short distances, like cell to cell through the plasmodesmata. Yeah, diffusion could work. But if you're thinking about long distance transport through the plant body, or even just through the leaf, it doesn't work. There has to be something else going on that's allowing for that more rapid transport that they could measure. All right. So then let's think about this idea. So then they're like, okay, what about the idea of bulk flow of substances from point A to point B? So bulk flow, here's the equation for it. The volume flow rate is equal to pi r to the fourth divided by 8. That's a cursive n. Okay, and then there's a delta P over delta X component. So R is the radius. And so for a plant, they were primarily focused on what's the radius of the xylem cells. So now we talked about how xylem, there's two like subtypes of xylem. One starts with a T and one starts with a V. Remember, what's the T word? And the V word? Tracheids and vessels. Very good. Which one's wider? Vessels. I always remember that because the V widens up at the top, so it's wider. Okay. And so vessels are wider, tracheids are narrower. And so the radius between those two is going to differ. But look at how it's r to the fourth. So what that's telling you is the flow rate is really sensitive to the radius. If you have a radius of 1, 1 to the fourth is 1. If you take a radius of 2, what's 2 to the fourth? 16. That's a huge difference, right? So the volume flow rate is super sensitive to the radius of the xylem. So that's an important concept. The delta P over delta X is another important concept. We're looking at a change in pressure over some distance, point A to point B. P is your pressure. N is the viscosity of the liquid, which again, you can look that up and plug it in, okay? So bulk flow is the idea of when you have some external force being applied to a body of water. It could be gravity, think about also like when you hook up a fire hose to a fire hydrant and turn on the water, and then the water comes shooting through the hose. That's bulk flow. Think about water moving in a stream. That's bulk flow movement. Yes. Yeah. So there's such a thing as root pressure, and it's kind of the opposite of how we think plants normally move water through their body. And so I'm going to talk about root pressure because it's kind of the opposite of how plants move water through their entire body. And it's only under certain conditions that you can get a buildup of root pressure. But yeah, it's a delta P over delta X idea when you think about that. So hang on to that thought. We'll get into it. So instead of Fick's first law, Fick is the one who did diffusion. I think it's pronounced Poisson. I never took French. I took sign language and Finnish and German. So I don't know French. Is that correct? You know French? Poisson? Okay. I'll have to write that down phonetically so I don't forget it. And so he came up with this idea to explain bulk flow concept of water movement. And when you do the calculations, it fits pretty well for long distance transport. The equation holds up well compared to their experimental measurements of how things are moving through the xylem in the plant over some long distance. So again, keep in mind, it's very sensitive to the radius, r to the fourth, not just r to the fourth. So that r value can really impact what's going on in terms of the flow rate. So another way to say delta P over delta X, that's a pressure gradient, okay, pressure gradient. Fick's first law, the delta C over delta X, that's a concentration gradient. In the bulk flow idea, it's pressure gradient. So they realized pretty quickly that if you're going to explain how water moves through the plant body, you have to factor in both ideas. You have to think about concentration, primarily the solutes that are dissolved in the water, because when a plant has its roots buried in the soil, is the soil giving the plant pure water? No. So there's water and there's dissolved minerals, hopefully, in the water. Gases, dissolved gases. So it is not pure. All right. And so you have solutes in that water that the plant is taking up. So you have to think about that. There's some concentration issues, but there's also a pressure gradient issues to think about when you think about water movement. And so I'm going to try to convince you of that. So here they're showing the idea of when you think about water movement through the xylem, you have to start in the roots. So let's just think about a typical plant that has its roots buried in the soil. The roots need to take in that water and the dissolved minerals, and it will happen primarily through the root hairs. Root hairs do the lion's share. The vast majority of water uptake is through root hairs, which are those very fine epidermal cells that are long and skinny, great surface area. They can take up the water and minerals. Then it has to get into the root area where the vascular tissue is located, and that's usually closer toward the center of the root. And then once the water gets dumped into the xylem, it's on a one-way transport up to the leaves, one way, unidirectional. They have yet to measure water movement in xylem going down, like from the leaves down. That doesn't happen. When water movement is occurring, it's unidirectional. And I don't know if let me just introduce that term right now. Transpiration is a fancy term of water movement through the plant body. So when you're talking about transpiration, it's a one-way unidirectional movement of water. Soil into roots, into the vascular tissue, up, out to, all the way up to the leaves, and then out through, what are the pores called in the two guard cells? Stomata, all right, and then out through the stomata as water vapor. So it has to shift from its liquid going through all the xylem. Once it gets to the leaf, inside the leaf, it's going to shift into water vapor. And then it exits out the stomata as water vapor. Okay, so when we talk about the movement of water, you have to think about osmosis. And I like to break osmosis up into a two-part definition. And both of those have to be met in order to talk about osmosis. Movement of water. The second part of the definition is through a selectively permeable membrane. If you don't have both of those conditions, you don't have osmosis. Okay, now a very simple way to get at osmosis is through kind of like a thought experiment of taking, I cannot say this word without thinking the wrong thing, taking a YouTube. What do we think about when I say YouTube? Amazing. But back in the day, that when you said YouTube, this is what you meant. All right. So you take a YouTube and you have a membrane at the base there, crossing, selectively permeable, and you make it so that the water can get through, but not the solutes. So it's selectively permeable, just water. That's the only thing that's moving through. You start the experiment like what they show on the left, where they put two different glucose concentrations on either side of that U-tube. And then they wait to see what happens. How is water going to move? And so on the right, you can see the result of that experiment. That water shifted from the left side and went into the right side. You could think of it like, often when you're taught in intro chem, for example, they'll say water will want to dilute out the higher concentration of glucose, and so water will move over there to dilute it out. And that's fine to think about it that way, okay? Well, the reason they picked a U-tube is that they want you to think a little bit about, you know, movement of water up the plant in xylem. And so this is kind of like moving up the xylem. It's when you have water moving up like that in a column, you're exerting gravity more now on this side, right? You have a standing column of water that's higher on the right compared to the left. And so you're going to have gravity impacts. This column of water is going to push against that membrane a little more firmly than the left side. So we have to think about that a little bit too. So what's going to happen is water is going to rush into the more concentrated side where there's more glucose, but there's going to come a point where the pressure, the back pressure on the membrane is going to be enough to keep more water from moving in. So do you see what I just said there? I'm talking about two different things. Concentration got water to move, right? So this imbalance in glucose, that's a difference in concentration, delta C over delta X. Concentration gradient. So water goes, oh, I'm going to move across and try to dilute out that high concentration of glucose. Okay, so that happens and happens, and now we have gravity influencing how many more water molecules can come across, because it starts to push and create that delta P over delta X impact. Okay, so first we talk about delta C over delta X, but eventually delta P over delta X comes into play. Have I convinced you of that?
So is it a linear relationship between pressure and concentration in terms of osmosis?
You can think of it that way. That's an okay way to think about it, yeah. So what we see is that movement of water with, you know, the water and the dissolved minerals. So in the plant's case, it wouldn't be so much glucose, it'd be all the dissolved minerals instead, okay? But that movement of water and the dissolved minerals through the xylem, so to actually physically measure that, like really take actual measurements, they started with, you can do it through doing the chemical potential of water. You can do those kinds of measurements if you want. And I'm just going to introduce this idea very quickly. You probably had this in some of the intro chem classes. So the chemical potential of water, when you define that, is the free energy per mole, the joules per mole. Okay. So if you put it into the context of the chemical potential of water and think about that U-tube thought experiment, you would say, well, osmosis is going to occur when there's a difference in the chemical potential of water on either side of that membrane, which is true because there's two different glucose solutions. So you can say, yeah, the free energy of water on the left is higher because there's less glucose in the way, so to speak. So you have higher free energy. The chemical potential of water is greater on the left than on the right because there's more free energy here because you have fewer glucose molecules. Then you would say water moves down a gradient from high chemical potential to lower chemical potential. And because we said that there's a higher chemical potential on the left of water, it's going to move from high to low. And that's another way to describe how water is going to move in this system, in this particular scenario, okay? But again, it's still affected by concentration. By the concentration, you can either think about it as the concentration of the water molecules on either side of the membrane or the concentration of the glucose on either side of the membrane. It just depends what works better for your brain, how you want to think about it. But there's definitely a difference in concentration on either side of that membrane, and pressure too, because once water starts to move and that water column goes up, you get that pressure coming back down on the membrane. All right, so you can actually experimentally measure what that pressure is. So if you set up that same experiment and then say, you know what, I want to measure what the back pressure is coming down against that membrane. And so what you do is you can actually put an instrument in there and you can apply pressure and find out what that amount of pressure that you need to apply to keep the water column the same. And that's how much pressure you're starting to generate in the system if you had let the experiment go. Okay. So there's ways to experimentally do all of this and figure it out. And the plant physiologists did that. And then because plant physiologists are wanting a more convenient way to take these kinds of measurements, especially when you're out in the field and you have to measure your agricultural field or whatever, and you're trying to assess water aspects of the plant. The chemical potential of water measurements, it's really not conducive to field measurements, like the practicality of taking measurements. So they came up with an idea to convert it to water potential. So they said, let's take the equations of chemical potential, let's do a bunch of derivations of it and turn it into a water potential situation. Now, I'm not going to derive all of that for you. I can if you want, but it's a lot of math and you'll be snoring quickly. All right, so I'm not going to do that. If you really want convincing, I can work with you on that. But they took the chemical potential equations and did derivations where they came up with water potential, which is the Greek letter psi and then the subscript W. So psi sub W is water potential. You need to know that. This is going to follow you now through the whole semester. It'll never go away. So what they ended up doing is they took the chemical potential of water and divided it by the partial mole volume of water. And again, I'm not going to ask you to memorize that. I'm just trying to convince you that they did it correctly. It was all legit. And what ends up happening is it allows you to measure the free energy per unit volume in joules per meter cubed. Yeah, the next slide will show you the derivation of it here. Okay, so if you take the chemical potential of water and divide it by the partial molar volume, the unit for that is chemical potential is joules per mole. The partial molar volume is meters cubed per mole. So then if you understand that a joule can also be expressed as a Newton times a meter. So if you just plug that in, replace the J with Newton times meter, okay, divided by mole, and then meters cubed per mole, and then do the cancellations, you end up with Newton per meter squared. Newton per meter squared. That is equal to the unit called a Pascal, which is a unit of pressure. Pressure is much easier to measure in practicality, in real life, than the chemical potential of a solution. That's a pain. But pressure of a solution you can measure much more easily. So that's the main reason why they did this. It's just easier to think about, easier to talk about, easier to measure, all right? So water potential is measured in units of pressure. Pascal is what it's called. You abbreviate it down to PA, and then often it's megapascals that they end up taking. The actual measurements are actually, big, megapascals. So sometimes you'll see an M in front for megapascal. Okay, so now we can kind of forget about chemical potential of water and start thinking about water potential. So if we phrase it with that idea in mind, what we would say is that water is moving from a high water potential to a lower water potential, so down a gradient. And that's valid to say that. However, we're going to find out that in the xylem, when you are looking at water movement, water potential values are actually negative pressure units. So in the plant body, when water is moving through the xylem, it's negative. And I'll talk more about that, all right? So water potential is usually negative. So now you have to switch your brain to the negative scale. All right. So if you want to phrase it that way, you would say water moves through the xylem from less negative water potential to more negative water potential. And that's still down a gradient, right? Because if it's a less negative value, it's higher, it's bigger than a more negative value. If you think about the negative scale in math, right? So I'll come back to that. We always measure this against a reference. By definition, they decided to pick pure water at atmospheric pressure. That's what they always measure it against. And if we think about that, they said, let's call that 0, a water potential of 0. Pure water is at open to air is 0 water potential. Let's use that as a reference. Okay, so water moves down a water potential gradient. You could think of it that way. It's true that it moves from a high water potential to a lower, but because in the xylem we're talking about negative situations, the negative scale, it's actually more accurate to say water moves from a less negative water potential to a more negative water potential. So there is, well, okay, so here's the actual equation, the water potential equation. This you do have to memorize, but it's easy. Okay, psi sub W is equal to psi sub P plus psi sub F. So psi sub P is your pressure potential, looking at what kind of pressure is building up in the system as water is moving, and where is there a difference in pressure, and how much of a difference. So pressure potential. Because we're talking about water, they often refer to it as hydrostatic pressure. Hydrostatic pressure due to water. The psi sub S component of this equation is your osmotic potential. It's actually talking about all the solutes. So the S stands for solutes, all the stuff dissolved in the water that's moving through the xylem. Okay, so solute potential. So you can see that water potential has a pressure component you have to think about and a concentration component. So that delta C over delta X, the delta P over delta X, it's still there. It's in this equation. All right. Now, if this were a graduate level plant phys class, I might tack on a couple more units to this equation where you would factor in a psi sub M and a psi sub G. G is gravity, M has to do with the actual component of the xylem matter. We're not going to do that because we're going to think about like an average plant, not like a giant redwood. All right, so we're going to think about a typical normal plant, tree, nothing massive like the awesome redwoods and sequoias. Okay.
Would those two other units make a difference with normal plants?
No, right. That's why they kind of said, yeah, for the typical plant, you can leave it off because it doesn't really fuss with the actual end result. But once you factor in these really outlier plants like giant redwoods or something, then that would make a big difference. So, okay. So, okay, I'm guessing when most of you took math class and you were presented with the first idea of the negative scale, they probably wrote it like this, where 0 and the positive goes off to the right and the negative numbers go off to the left. Is that what you're probably used to? So for the longest time, I apologize to all the previous students. I would write it on the board like this. And I realized someone finally said something to me. I'm like, oh yeah, I guess in math they do it this way. I think it's because I'm left-handed. My brain just flipped it. And so I always wrote it down this way because left is positive, right? The left. So anyways, so if there are some lefties in here, that might make sense. So I still keep it just in case you're a lefty and you flip things like I do. There's been so many cases where I'm doing something in my real life and I'm like, think like a right-hander. How would they do it? Because so much of what all the stuff that's made and you manipulate is all for righties. It makes it, that's weird. Anyways, let's look at the negative scale. So you have 0. So -1 is a bigger number, larger number than -6 and -9. All right. So the closer you get to 1, that's less negative. Further you get from that 0 mark, the more negative you go. Okay, I'm just refreshing your memory here on the negative scale. All right, so now here's a scenario where they drew a beaker that has some solutes in there. Let's say it's glucose dissolved in. And they did the calculation and they said that beaker of glucose solution has an overall water potential of negative 0.15 Pascal. And then they said, what happens if you drop a plant cell into that beaker of glucose solution? And they say, well, let's measure the water potential. Let's say it's negative 0.25 pascals in the cell. So water potential, water is going to move from less negative to more negative. So if you dump that cell in, now remember that cell has a cell membrane, so it's a selectively permeable membrane, and there's a difference in concentration across that membrane compared to what you see in the beaker and what's inside the cell. So you dump it in, how will water move? Will it move into the cell or out? Into. It's going to move from less negative water potential, negative 0.15 is less negative than negative 0.25. You plop that cell in, water's going to move from the beaker into the cell. Okay. So that's going to happen. It's going to keep happening until you get that pressure. The delta P over delta X is going to start to weigh in on this. And there's going to come a point where there's going to be pressure built up pushing against the cell membrane that's not going to allow any more water movement into the cell. So the difference in concentration certainly allowed for the water movement, but then the delta P over delta X is going to come into play eventually, and sometimes very quickly. So now, you know, nowhere on here did, like, you just know the overall water potential of these two components. We don't know exactly what the size of P and the size of S is for each of these. Okay, they didn't give us that information. We just know that the overall water potential is less negative in the beaker compared to in the cell. And based on that, water should move into the cell, and that's correct. But you're going to reach a point where the pressure is going to come into play. And so that's going to start to modulate the situation. Eventually, if there's going to be no more net water movement eventually. If that's the case, you're going to end up with a water potential in the cell and the water potential in the beaker will equal each other. It'll be the same number, some negative number. And it's going to be somewhere in between 0.15 and 0.25. But I don't know what it is. Okay, they didn't show you any of that. So here, let's just look at this idea. You have a beaker of pure water. So that's your reference. It's open to air. There's no membrane covering that water. So it's open to atmosphere, it's pure. Under those conditions, we know that the overall water potential is 0, just by convention. Okay, so just keep that in mind. Here, they're saying this solution has 0.1 molar sucrose. So it's important that you appreciate 0.1 molar sucrose, that's concentration. Molar is moles per liter, right? Okay, so 0.1 molar, 0.1 molar, M is for molar, and that, the units for that is moles per liter. That's not Pascal, right? But moles per liter is not Pascal. So just because you see, you can't equate this to, like I've had students in the past say, oh, well then the psi sub S is 0.1. No, no. That's molar. That has nothing to do with Pascal. You would have to convert it to Pascal somehow in order to do that. So just keep in mind, 0.1 molar, that's moles per liter. You have to do a special equation to convert what 0.1 molar would be to calculate psi sub S. And you'll actually do that in lab. And it's a simple equation, nothing terrible. You just need a few extra units to plug in a short equation. So you will figure that out, but don't equate it. 0.1 molar is not the same thing as your direct psi sub S. You have to do a short equation to get there. Okay. So here they're giving an example. Well, I think I have a better example. Let me see. Oh, one other thing I wanted to point out. So we often talk about, when we do these thought experiments, we'll talk about a flaccid cell. If you see that in a word problem, what that means is that flaccid means there's no hydrostatic pressure being exerted against the cell membrane and cell wall of this cell. So that, by convention, if they say flaccid cell, that means size of P is equal to 0. Okay. So somebody did a calculation where they said this cell is flaccid, so it must have a 0 megapascal size of P. They somehow measured the solute concentration in there, and they ended up doing the equation, and they said, okay, that has a size of S of negative 0.732. And so the overall water potential equation, you add those two together. And when you add those two together, you get negative 0.732 megapascal. And then they said, okay, let's look at the beaker. And they did the calculations. And is that from the previous one? So the 0.1 sucrose solution was negative 0.244. Yeah. So what they're showing here is that you can manipulate the water potential equation if you want and solve for size of P. Right? So you can do that. I'm not really going to get into that too much. I'm more interested that you understand the overall water potential. You know, psi sub W is equal to psi sub P plus psi sub S. And so we're going to work through some of this, you know, a couple of times. I'll give you some examples that we'll work through. And then in lab, you're actually going to do a water potential experiment, which is actually going to be done with one of my favorite foods, a white potato. And so we're going to get you some big whopping baked potato sized potatoes, and you're going to do a simple experiment. It's really kind of funny how it's super simple, and yet it gets across some very profound ideas of water potential. Okay, so you'll be setting that up next week. So you may be sitting there going, who cares? What's the big deal about water potential? Why would plant physiologists even bother? Sounds like a lot of math. All right, so they are doing it for a reason. It helps them assess the water status of the plant. Okay, so now with the current technology, you can go into your agricultural field, your grow field, and you can have the fancy equipment that you bring with you, and you can assess water potential on the fly, right in the field. And so a well-watered plant would have an overall water potential, a psi sub W, of close to 0. Someone put -0, whoever the artist is. It's like -0? Anyways, so somewhere between 0 and -1-ish is a well-watered plant. If you take your water potential equipment and you start to see it dropping -1 and worse, you know that that plant is under some water stress. And then you can adjust your irrigation appropriately, right? So this graph is looking at, well, what happens if you have a well-watered state versus a plant that's under water stress, or maybe a desert adapted plant? What's going on there? And so here are some, it's not a total list, but it has some important processes that plants have to be able to do. And so where you see the bar really fat here, that means that everything's cooking along good. It's happening. So we got near 0 water potential. You got good cell expansion. There's enough turgor pressure, hydrostatic pressure for cells to enlarge. You get the cell wall synthesis cooks along, protein photosynthesis cooks along. Then you see stomatal conductance. That's how wide open the stomata are. Are they really narrow or big? So if there's good stomatal conductance, that means your pores are pretty much wide open. If you have poor stomatal conductance, that means your pores are closing down. Okay, more friction effects when you close down, so the friction really weighs in, and your conductance isn't so good. All right, but wide open, yes, good conductance. Here you see photosynthesis crashing. with poor, with stressed plants, water potential getting more negative. Well, that's a big deal, obviously. If you're trying to grow a crop for a livelihood, you don't want photosynthesis to tank in the middle of the day. And so it has a huge impact on photosynthetic rates. Here, we're going to get into these ideas next time. Abscisic acid is a hormone. You can see that as the plant is getting stressed, it upregulates its abscisic acid, and it also upregulates solute accumulation. So we'll get into that. Plants have a way of working the system if they have to. And so those two on the top are their ingenious adaptations. So we'll get into that next time and continue on Wednesday. We don't have class Monday, but on Wednesday, we'll keep tackling water potential and water movement.
What kind of
They actually have